All right, so it's the last talk of the second block of talks. We're very happy to welcome Bruno Vallette, who will tell us about deformation theory of cohomological field theories.
Thank you very much. Thank you very much for the organization, for the invitation, for being so patient with an old guy who doesn't know how a computer works. That's not quite true. I mean, but you see, I hope that's okay. So you see, I'm writing on my iPad, and so somehow I'm giving a talk as if this was a blackboard or a whiteboard. But in order to save time, I already wrote a few things, but I didn't want to write too much because then it's not very natural. Okay, so today I would like to explain you what we did. When I say we, is Vladimir Volodya-Lutsenko, Sergei Shadrin, and Arkady Weintraub, on the deformation theory of cohomological field theories. One forward before to begin. I already, as you did, I already experienced giving courses through computers, etc. My feeling is that I'm playing the piano without being able to hear what I'm playing. So please feel very free to ask questions, stop me, etc. Otherwise, it's, I think, boring both for you and for me. Okay, please. Bon, so I wanted to first start with the state of the art of these five big words, okay? Deformation theory and cohomological theories. What do I mean by that? Well, let's be fancy, and let's start with arithmetics. So Grothendieck's program, esquisse d'un programme, purpose was to study the absolute Galois group via the geometry of the moduli space of curves with marked points of genus G. Well, I'm being very vague about this because there are guys which are more experts than me here, for instance, Geoffroy, etc. Okay, but this is maybe a kind of, it's a very good motivation anyway. Bon. Of course, Grothendieck did not fulfill his program. And several years after, Drinfeld, a very clever guy too, he tried to get close to Grothendieck's ideas, and he coined some notions of what he called the Grothendieck-Teichmüller groups. There are several of them, profinite, pronilpotent, etc. Bon. The definitions of Drinfeld are quite algebraic. They seem to be a bit further from geometry than what Grothendieck had in mind. Anyway, they are related to the genus zero moduli space of curves. Bon. And then a few years later, by looking at the geometry of MGN. Alors, first, MGN is not compact. I will explain in details all of that later. Okay. So first, MGN is not compact. Of course, the points can come close to one each other, and then this explodes. So you need to compactify that by introducing some strata. And this is what this MGN bar means, is the Deligne Mumford-Knudsen compactification of the moduli space of curves. Bon. But when you look at that, you see that you're using operations, namely composing, contracting curves, which are close to what Grothendieck had in mind. If you read closer or read again, Esquisse d'un programme, Grothendieck is already mentioning that in his esquisse. Bon. And when you look at this geometry of this guy, this very particular example, Getzler and Kapranov in '94 came up with a general notion of a modular operad. So this is a notion which extends the notion of an operad, which is the main topic of this conference. But there are something more. Okay, by modular, you have an extra structure that you cannot have, you do not have on operad level. Okay, fair enough. So this is a rich domain. At the same time, '94, you had Kontsevich and Manin, who said, look, let me put it that way, because I don't know which one comes first between Kontsevich, Manin, and Getzler-Kapranov. Okay, since MGN bar forms, say, a certain type of operad, what's quite interesting is to look at algebras of that operad. And this is what is called, what they called cohomological field theories, okay, which I abbreviate by CoFT. Well, and why are they looking at this kind of algebraic structures modeled by the moduli space of stable curves? Because the Gromov-Witten invariants, they respect the relations of this kind of algebras. And this structure appears in quantum cohomology. And after that, the notion of coFT appeared in many other domains, symplectic geometry, mirror symmetry, integrable systems, etc. So this is a notion which is quite ubiquitous in mathematics. Okay. Now, one could say that the story not ends, but one branch of the story ends here. Because here, if you look closer, that's what we're going to do in the next minutes. The Grothendieck-Teichmüller group is actually not quite completely related to MGN. It is more related to the general notion of modular opérade. So far, it is not using the very structure and the elements of MGN bar, okay? But more the general structure that it satisfies. But now, if you look closer to MGN bar itself, okay? Not any kind of modular opérade, those combinatorics is based on graphs. What do you see? Well, you see that when you look at the cohomology of MGN bar, inside this cohomology ring, well, first you would like to compute it. Congratulations. Well, if you can do it, that's an extremely difficult question. So the first step is try to recognize some guys there. So this is what here I denote by tautological classes. So what are tautological classes? These are some kind of classes that are well known in this cohomology ring, okay? And each time one wants to compute, not maybe each time, but a powerful method to compute a cohomology ring of a topological space is to say, look, guys, here are some great elements in this ring. Okay, so if we have these elements, we can multiply them. So we can look at the free algebra on these guys. Okay, and then these guys, maybe they satisfy some relations. Oh, cool. So we may have a tentative presentation of this cohomology ring. Okay, fair enough, etc. And maybe if we have enough generators and enough relations, we can compute the cohomology ring. Well, here, the tautological classes do not give the full cohomology ring of MGN bar. Okay, but still, I'm not good enough expert to say we get close, but we have a lot. So one can anyway use these particular characteristic classes of MGN bar. And that's what Giventhal did, and this was used by Telemann later after. Giventhal coined a group which was acting on coFT using the particular properties of these topological classes. And this group was used later by Telemann to classify semi-simple coFT. So it's a group which is quite important in this theory. Okay, so now before to go to blue, I want to hide it as much as possible. Okay, and who's the next great guy I want to mention in this story of giants is Thomas Wilvar. So not everything was done after Drinfeld and Kontsevic's work on this domain. For instance, Kontsevich introduced several graph complexes, and graph complexes, their homology is extremely difficult to compute because of the combinatorics of the graphs, because of the genus. And Thomas was able to show that, so you look at this graph complex, a certain graph complex, we'll recall it later on, and it actually forms a Lie algebra that you can integrate to form a group. And Thomas, of course, this is a big mistake. So someone should have complained, and then I think I can correct it. Let me put that here, check. Okay, how do I get the colors? This way? No. Nah. Please. Alors, give me 1 second, I'm trying to get some colors. Bon. No. So, yeah, cool. So, okay, good. So, please, first mistake, which is good. Nah, it's a big one. No, not Thomas, unfortunately, was not able to compute the full homology of this graph complex. He was able to show that H0 is equal to the Grothendieck-Teichmüller Lie algebra or group if you integrate it. Okay, we'll come back to this point later on. Okay, that's it. So we're here today, more or less, and somehow there is a slight discrepancy. Okay, on the left-hand side, I was saying that we do have the general combinatorics of graphs with genus, and they give rise to Grothendieck-Teichmüller groups a la Drinfeld. Okay, fair enough. This was the left-hand side. And now on the right-hand side, now you have one very particular guy coming from geometry, the classes of MGN bar. And these guys allow you to coin a group, which is Giventhal-Telemann group. And the question we asked ourselves with Arkady, Volodya, and Sergei is, can we merge these two approaches? Is there a way to unite them because they seem to be closely related? Well, they actually are. So if you are patient enough, I think that by 4 p.m. here, you'll have the answer. Okay, so let's go and let's develop the theory. So I try to divide this talk into 3 parts. First, I would like to recall what is the general domain of operatic deformation theory. This will allow me to recall the methods we're using. Then we're going to attack cohomological field theories. And so to apply the general operating methods to cohomological field theories. And yes, thank you. So I'm writing too much in French. So here there should be an extra M. And then, of course, now that we will have developed the depth theory of coFT, we'll be able to study universal and seminal symmetry groups. And at the end, the biggest of them will include both Grothendieck-Teichmüller and Giventhal-Telemann. Is there any question right now? No. Bon. Let's continue. Okay, so what is, say, deformation theory? Okay, so a first and rough introduction to deformation theory could be something like this. Of course, you heard that before in the talk of Joss and the other talks. Let me just do that quite quickly, and I won't talk about the formal moduli problem, etc. So, okay, you have a space A, say, and of course, I'm being very vague on what is a space. That could be a topological space, a manifold, or whatsoever. And on this space, you want to check some kind of structures of type P. Of course, MatCal P means something for me, but okay. And you want to check, how many structures of type P can A accept? Okay, so bon, it was realized by many people over the last century that very often in characteristic zero, of course, there exists a differential graded Lie algebra or an L-infinity algebra, which from the homotopical point of view, these two notions are equivalent. Since the operad L-infinity resolve the GD both have the same homotopical properties. Okay, so associated to A, the space, so to the space A and to the structures P. Give me 1 second. Okay. So associated to the space A and to the structure P, you very often are able to coin a DGD algebra such that now you're looking at the Maurer-Cartan equation. This equation. This is the Maurer-Cartan. No, yeah, we have to go a bit further. So this stands for Maurer-Cartan equation. Okay, which is the classical Maurer-Cartan equation that you know of connections, etc. Okay, and the ultimate goal is to find the DGD algebra. Those elements, those Maurer-Cartan elements, are in 1-1 correspondence with the structures you're looking for. And of course, if you stop here, this is interesting, but not that interesting. What you want is not all the structures of type P, but the structures of type P up to some natural equivalence between them. For instance, if you're looking, let me look at the example I wrote before, below. If you start from a vector space or DG vector space, you can check, let's say, I don't know, you have a 10-dimensional vector space. You want to check how many associative products you have on that. Okay, well, fair enough. But this is not really, this is interesting, but you can go a bit further and look at associative products up to isomorphism, for instance. Okay. So how many different non-isomorphic associative algebra structure you have on it? Okay. So now these equivalences should coincide to a certain gauge group, which is well defined when your DGD algebra is complete with a certain filtration. You have an infinite series, but let me hide all these technical details under the rug. And then you take, so the degree 0 part of G, you take the Becker-Campbell-Hausdorff formula, which is an infinite series, but it is associative and unital. So this defines for you a group, a gauge group, which acts on Maurer-Cartan set, on the set of Maurer-Cartan elements under natural operations. Okay, and you hope that your equivalences coincide to that. Okay, so since you had the talk of just before, let me just quickly recall what you saw in his talk too. In the case of when A is vector space P associative algebra structure, it turns out that good DGD algebra is given by the product over n of linear maps from A times n to A. You equip that with what? Well, here you have maps with n inputs, one output, so you can plug them in all possible ways. This is the star product, and this star product is Preli, okay? Here I won't use the cohomological, which is perm. So this is Preli product, fair enough, and Preli means before Lie, that is, if you skew symmetrize it, so if you skew symmetrize it, you get a Lie product, okay? Okay, so presented that way, you'll recognize, but I put brackets, the Hochschild-Cauchy complex. And now if I look, we should have a discussion on which degree, which homological versus cohomological shifted or not degree we put on that guy. But let's say if you have a guy of arity 2, okay, so here I put degree 1 minus n, where 1 minus n is the arity, where n is the arity. So a guy of arity 2 here, which satisfies the Maurer-Cartan equation. Okay, so here. Okay, then have a look. What is D of alpha? Alors D is the derivative in this home space, the big home space, in this big home space, okay? So this is this D. So now D of alpha means that you should have this, which is equal to 0, which is the RT2 part of this equation. It means that D is a derivation. Alpha star alpha gives you left comb minus right comb. Okay, so it says that your product is associative. So yes, sure. Here, a Maurer-Cartan element in this DGD algebra is nothing but a DG associative structure only. So we have what we want. Okay, but there is a slight thing. Okay, I have been not cheating, but I looked not at all Maurer-Cartan elements. I said, well, if I restrict to this degree, I get that. But in general, if I take the degree of A and the induced degree on the home space, what I do get is a Maurer-Cartan element is a guy which is made up of a collection of maps for any n, which satisfies the Maurer-Cartan equation. And this is nothing but an A infinity algebra structure only. So here you see there is a passage from, I would say, classical structure to homotopy structure, infinity structure. And this should not be seen as a surprise. There is a very good reason for that. It comes from, so this, the Hochschild-Cauchy complex, comes from a certain deformation theory. It is the deformation theory of morphisms of operas. So that's what we developed with Sergei Merkulov some years ago, in which generalized the deformation theory of morphism of commutative algebra. So when you have a commutative algebra, in particular case, it is an associative algebra, which turns out to be the arity1 part of an operad. Okay. Well, so I will not recall this, but just to say what are the key elements in this setting. The key elements are, you want to derive the functor of derivations, okay, between commutative algebras. Alors, derivations are surely abelian, but the categories are not. So the category is the category of commutative algebras, okay? So you have a non-abelian, so that's why we are here in the domain of Quillen. That is, we are in the framework of non-abelian derived functor, okay? Well, but in the domain of non-abelian derived functor, what are we using? What is the input, okay? When we are looking at abelian derived functor, we have to use projective resolutions. Well, we have to use here non-abelian projective resolutions. These are cofibrant resolutions, usually quasi-free with a good triangulation on the generators whatsoever. That is here. We start from the operad as of associative algebras, okay? A structure of an associative algebra on A is a map from as to ND. So in order to derive this, so you see before, below, I have to take a cofibrant replacement of as, that is the operad A infinity. And in the end, the algebra I'm considering is the derived derivation. That is, I replace A infinity as by A infinity on the left-hand side, okay? Bon, since it is a conference on operads, I'm quite quick on this. A infinity is produced by the Kobar construction, the causal dual of as anti-Schrick, so this was already mentioned in the talks before. This is the free operad on asymptotic, to say it quickly, okay? Which means that here we have an isomorphism with just maps from asymptotic to end of A. And asymptotic is one-dimensional in each arity. That's why we get the shape of this guy, okay? Now I would need to unravel the co-operadic structure on asymptotic to get the Lie structure here, or the pre-Lie, or the Lie structure. Okay, it gets it. Bon. So this is the general framework of deformation theory of morphism of operas. And an important example after our paper with Sergei was the case of the deformation complex of the embedding of shifted version of the Lie operad into the famous Gras operad of Kontsevich. And that's what Wittwauer computed, and he proved that H0 is GRT1. Okay, I will review this. So just have this in mind. Okay, now things can start, and once we have this in mind, we'll try to copy paste, adapt this method to cohomological field theories. Okay, so let me record quickly the guys that we're interested in. Okay, we have the module. We consider first the moduli space of curves of genus G with n-marked points. Okay, so well, and then as I was saying before, this is not a compact space. So Deligne, Munford, and then Knudsen considered MGN bar, which is the moduli space of stable curves. And this is where the compactification comes from, of genus G with n-marked points. So I try to draw a picture. So you see, here you have curves. I should maybe have written curves like this with some genus, or I don't know, etc. And so on and so forth. Okay, and then you glue them. Okay, and then you glue them on some points, and then you forget these marked points. Okay, so the marked points cannot be on some crossing here. Okay, now if you look at what you're doing here, you have a space which is stratified, and the stratifications are given by graphs. And this compactification is operatic in nature. Why? Because now you can consider, say, two curves with two marked points, and one you view it as the input, and the other one you view it as the output. And you can plug the input inside you can plug the output inside the input, forget these two marked points, and you get, again, a stable curves of genus G plus G prime with n plus n prime minus 2 marked points. Okay, so this is very operatic. I knew I had left that. So let me try to write it. So if you take, say, a curve like this, okay, so with some marked points, try to show that. Okay, so marked points here, here, see here, here. You need to have at least two at each components. So let me draw another curve here. So let's say you have a marked point here, and I want to view it as somehow as the input numbered I. Okay, if this is 1, etc. And now let me come with another curve. Okay, and here for this other curve, I have a point G here. Okay. And then what you want to do is you want to erase this pointer. No, do not erase so quickly. So in the end, you're going to come up with something like that, okay? So this is the composition of curves. And this is very operatic, okay? Inputs, outputs inside inputs, okay? There's another thing one can do. One can start from a certain curve, okay, etc., with some marked points, okay? But you can also glue 2 points together. So let me maybe do something like this, okay? Now you can glue these points together and forget the marking. Alors, I will again make a mistake. Okay, so the marking is going, now we're going to have something like this, okay? So let me say, do something like that. Check, okay. So this is the kind of operatic structure one has on the curves, okay? And this was made into a general definition. So once you see this, when you see the geometry of the moduli space of stable curves, it's Kapranov, 94. They came up with the following general notion. So this came much after the definition and introduction of an operand. Okay. So their main example, their toy model for modular operand is, of course, the modular space of curves. Well, so what do you take? You take a collection, as usual, a collection labeled by G, the genus, and the arity, number of inputs. I loosely put an n square bar. The bar means that you have some restrictions. You have the stability constraint, which tells you cannot take anything when G and N are low, okay? Let's not make this explicit today. That's not the point, okay? Of course, this collection can live in any symmetric monoidal category, okay? Of course, here I'm going to look only at the case where my symmetric monoidal category is topological spaces or vector spaces, okay? And then what is the modular operand? You ask that you have two operations, a certain composition of operation, okay, which is this circle ij. In classical operand, we have only circle I because there is an output and I stands for the input, okay? So here, no, I have to specify what is I, what is j. Here, if you remember the example before, the first curve, I look at the point labeled by I and the second curve by j, okay? And this psi ij is the contraction map, okay? I did not write the such a that, I leave it as an example, as an exercise. So this such a that is, you look at what the composition and contraction of modular space of stable curves, what do they satisfy? Then you'll get the exact relations of this guy, okay? So of course, as an example, and that's what we want, this definition was coined such a that. Okay, so MGN bar is topological operand in topological spaces. And since the homology functor is a monoidal functor, so for instance, for me, the coefficients are Q here, you get that the homology of MGN bar is an operand in graded vector spaces. Okay, no. Okay, so what do we want to know now?
Bruno,
Vas-y.
there is a question in the chat.
Yeah. Attends, est-ce que je peux? Attends, Zoom, il est où? Zoom, on y va.
Philippe, he's referring to your pictures above. Philippe is asking if the psi ij, are there, so he's saying, are there supposed to be two marked points on that edit curve part?
No. What's, okay, here, I have, yeah. So, no. Yes, I want to glue, here it was I, here it was J. I want to glue at IJ and then forget these guys. Does this answer his question? Okay.
I think I was just confused about the two that were on that curve. At the bottom.
No. I want to say there is no. Yeah, I want to say there is no. No. You come with a. Let me try to draw it like this. Okay, something like that. Sorry.
Thanks.
It's more clear now. Okay,
Yeah.
sorry. Okay, good. Okay, so what do I want to say? Yes. Okay. So now we have the general notion of a modular operand. We would like to do the deformation theory of that. Cool. Let's apply the usual operatic method. So what does it mean? First, the trick is to encode the notion, your notion, now modular operand, previously it was associative algebra, with an operand. And then there is a subtle point that I would say every operatic guy made a mistake, except Dan Petersen, that, hey, you want to encode the equivariance of the operation of the modular part, which I, of course, didn't write above, okay? These operations circle I and psi ij are equivariant with respect to the bijection of the sets 1n prime. So you need to, so this is subtlety, but this is very important. I think that very few people notice that, so nearly nobody, and it took quite some time for many operatic guys to understand that. So the idea is what? You want to coin an operand O, okay, such that O are, such that O algebras are exactly modular operands. Okay, so if you want to have a, if you want to see what this looks like, your operad is generated by what? You have your I'll try to write bigger. Sorry, give me 1 second. Ij. So for each ij, conceptually speaking, circle ij is an operation which takes two guys and produce one. And then you have to label this input and output accordingly with some elements of a groupoid. Okay. Similarly, what is the operation xi ij? It is an operation which has one input and one output. Okay, fair enough. So O is a groupoid colored operad which admits two sets of generators, one binary, one unary. Okay. Now you have to trust me because since I'm cheating from the beginning, I have to be coherent and continue. The relations of circle ij and xi ij, they are quadratic. Okay, so here you have to believe me that the relations are quadratic. Okay, so which means that since this is quadratic, you can apply the causal duality theory to it. Oh, okay. Then you're going to tell me, oh, does the causal duality theory exists for groupoid colored operad? Yes, thanks to Ben Ward, who wrote this. So this is cool. Now we can consider the causal dual of O, which is O anti-Schrick, which is a groupoid colored.
Bruno,
Wait.
I think I don't know what a groupoid colored operad is.
Okay. Usually, okay, good. No, good. Usually what we have is we have operads which are colored by sets. Okay, which if you want, it's a category where you have no morphism. Okay, now you can label the inputs and the outputs of an operad by the elements of a groupoid. Okay, so you label it by the elements of the groupoid, but of course the data of the automorphism of the morphism you keep it within the data. Okay, and this is why you're going to encode this way the equivariance of the circle ij and the xi ij. It's very crucial. Is it okay like this?
Okay, but you don't need to do that for the usual
Yes.
colored operad that controls operads.
Yes, of course. Yes. Many people slipped on that point. Yes, you need. Exact same way. There is a place where you don't need to do that, is when you want to encode non-symmetric operads. Well, non-symmetric operads have no action of the symmetry group. So yes, fair enough. You can encode them with just colored operads. That's what van der Laan did in his thesis, and he developed causal duality theory of set theoretically colored operads. Okay, so each time you have a type of operad where the structure maps, the structure compositions have some equivariance property. If you want to encode it on the higher level, you need groupoid color. It's a very nice idea. It's a very nice idea. Yes. Okay, so you continue. Okay, so maybe I won't do all the details. Okay, but then, so Ben Ward was very much interested into this causal duality theory of groupoid colored operad because he wanted to get the notion of modular operad up to homotopy and get massive products in graph cohomology. So we won't go in this way. Now we'll go in another direction. Each time you have something like this, okay? Each time you have your favorite causal morphism between here to here, what do you get? You get, so what is an O algebra? It's modular operad. What is an O anti-Schrick operad? Well, you are quite lucky. This is a modular co-operad. Okay, actually there is a shift, so I should write shifted, but I think I will forget that. And now, as usual, I want to say, each time you have a twisting morphism, it gives rise to a certain adjunction, which is bar commun, okay? So hold on, bar goes from operads to coperads, and you have this, always, okay? And they are adjoint, and the left adjoint is the omega. So here, unfortunately, it's written in the right. Okay. Alors, you know these guys, huh? If you start from a modular, alors, more or less, you know these guys. If you take, so this is a remark. So if you go back to Gessler-Kapranov's paper and the papers that go after, if you take the bar construction of a modular operad and you take its linear dual, that's what people call the Feynman transform. Okay, so you have, so these examples, for instance, falls into this general pattern of operatic categories, lack of man-words of Heyman categories, Markle-Batanin, etc., etc. Batanin-Markle, etc. Okay, but anyway, so but it's not written with the language of colored operas. Well, anyway, I don't think there's much novelty here. I just want to put that in a general kind of idea. Okay, and I want to apply this. So we want to apply this because now what can we do? We can iterate. If you want to see everything, okay. If you iterate that, you can always do bar cobar of a modular operad and consider the co-unit of adjunction. So this is a modular operad. You can do the co-unit of adjunction and you get a functorial replacement for any modular operad, okay? Of course, you see where I'm going. I want to apply that to our beloved modular operad of a moduli space of curves, and then we will get the notion of coFT up to homotopy. Well, before doing this, I forgot to say what is the endomorphism operad here. Maybe I can draw it quickly. So what is circle ij here? So if you start from a space A with a pairing, keep in mind that when we're working with modular operad, there is no input, no output. So we need the pairing. So if you have AI, AN, and some BI, B1, BN prime, what is circle ij? Circle ij is you pick AI here, and you're gonna do the bracket with BJ, okay? So you remove this guy, and you do the bracket of the two. So you have two less guys and an extra constant which comes in front, etc. And psi ij is psi ij, you have AI, AN. Of course, here in the middle, you have AI, you have AJ, and you do the pairing of these two guys, check, and you remove them. And that forms a modular operad. So now you can look at morphism of operads. No, you can look at the morphism of operad from the homology of moduli space of curves to the endomorphism operad, and this is a coFT, okay? Alors, I wrote the def complex before, really, that's what I wanted to do. I didn't write it. Okay, I planned to write it. Okay, so let me look that too, okay? And of course, so sorry, I planned to write it, but I didn't leave enough space. Okay, now instead, if you want a homotopy coefficient, no, I wrote it. Where is it? Excuse me. No. I thought I had, yes. Okay. So let me do it right now. Okay, and of course, if you want to have the notion of homotopy coFT, what do? You take bar, cobar of homology of this instead of that here, okay? And that you get the notion of a homotopy coFT. Well, so usually, in general, we replace this by the causal dual, but there's no causal duality theory for modular operads themselves, okay? Not groupoid colored operads. So we cannot, I don't know how to reduce that today. Anyway, let's continue. Okay, so now what is a deformation complex? You do the usual business. The deformation complex is some kind of home from B omega, the homology of moduli space of curves, to endomorphism of A. So this is isomorphic to home from bar construction of the homology of n bar to end of A. And this is what? Well, you're going to take the bar construction of the homology, okay, take its linear dual, and at any input, you put A. So in the end, you get some kind of graph. You see, that's the picture which is below. You get all the graphs, okay, where your nodes here, they get labeled by a certain cohomology class of MGN bar, and where your inputs, they are labeled by A. So the deformation complex of homotopy coFT has this shape, okay? Now you can ask yourself, okay, good. When I was looking at the def complex of operad maps, it was a pretty algebra. What about here? So what is the structure of this guy? Well, you do what you usually do. So you take the totalization of your space. Each time you have a modular opera, you can take the product of its components, okay? So D gives a D. You take the sum over all the circle I, and you get a bracket, okay? And now you take the sum over all ij of psi ij, and you get a product, an operator delta, which is an unary operator delta, okay? Bon. And now here, equipped with this, you can look at this Moror-Cartan equation, okay? So now you look at the relations of that. Okay, first, all these operations have degree -1, okay? Then this guy is a Lie bracket, a shifted Lie bracket, and this guy is an operator which squares to 0. So let me call this structure a shifted delta Lie algebra. D'accord? Shifted delta Lie. Shifted because all the structure operations have degree -1. Delta means that delta is a derivation with respect to the bracket, and it's skew commute with D. D is a derivation with respect to the bracket. Okay, and here, since we have no input, no output, the bracket is actually graded symmetric. Okay, you have no Prélie. That would be beautiful because when you have a Prélie product, you get much simpler formula for all the Lie theory. Okay, but here you have nothing better than Lie. Okay, it doesn't split. Oh, that's fine. Of course, here what you can look is at the master equation. So why master? Because now there is a delta. Okay. So I left some space. Yeah, I will put some more space now. Okay, so let's look at now in our beloved algebra here. So GA, okay, so I will call it GA now. So this is a shifted delta Lie algebra. And when we look at Moror-Cartan master equations here, the solutions are what? We can look at solutions which are just vertices, okay? You don't take any sum over fancy graph whatsoever. When your Moror-Cartan guy is just concentrated on vertices, you get exactly the notion of cohefty. If moreover you look at guys which are labeled by cohomology 0 classes, you get topological field theories, okay? And of course, in general, you get homotopy cohefties. So you came up with very good delta Lie algebra, which encodes the properties of homotopy cohefties. Okay, so what I wrote here, I already said it. Now this. Yes, but no. We are used to do deformation theory with DG Lie, not delta Lie. So what can we do? But there is a functor from here to here. So there is a functor from here to here. What can we do? And this functor amounts to say, look, guy, we could take, let's say curly D, which is D plus delta, right? Both have degree 0, okay? So I can now forget this. I can take the sum of these two guys as if I was doing the inverse of a spectral sequence. Anyway, and now if you look at that, delta bracket, now this forms a DG Lie algebra, okay? And then now this equation becomes equivalent to curly D alpha plus 1/2 alpha alpha equals to 0. That is your classical Moror-Cartan equation. D'accord? Okay. So now when you're looking at solutions to master equation, it is equivalent to looking at solutions to the Moror-Cartan equation. And in this way, you can do the old fashioned, which goes back to, I don't know who, Fegin and then further, infinitesimal deformations, formal deformations, etc. So you're in a good setting. Okay, so let me give one example. So there was a paper by Pandaripande, Zonkind, and an appendix by Dan, where they create very interesting cohefty structure from topological field theory structures. You start from the cohomology algebra of a genus, a curve of genus M. Okay. Okay, it carries a topological field theory structure. So it gives you a solution to the master equation. Now you want to perturb it, okay? Okay, so what can you do? Well, you take what is called a minimal class, which for me is, well, you interpret it as primitive element with respect to the co-operad structure, okay? You see the homology forms a modular operad, the cohomology forms a modular co-operad. And now thanks to this alpha, you and the element of A, this formula is not precise at all. You'll find it on the paper. But you coin this kind of guys, one vertex labeled by some elements of A. And the proposition is that now, you see, you started from your alpha, which was your TFT structure on the cohomology algebra. And you perturb it with a guy which is actually a tangent to alpha. This lambda is tangent at point alpha of the Moore-Cartan variety, which encodes your coeft. So this is an infinitesimal structure. It turns out that because of the fact that you took a minimal class, etc., this infinitesimal structure, this infinitesimal deformation is actually a global one. Okay, so this stated in this language. Okay, but now, since we're able to phrase this construction within the depth theory of coeft, we're able to extend a little bit this kind of examples, and there maybe should be more, but now there is a framework for this construction. Okay, so now I think there is what, 10 minutes or something like that. Tell me if you're in a hurry. Okay, so there are two forthcoming problems. One that I did is, and I should write it. Now, let me pass to, I was doing some Z grading. Okay, I was doing some Z grading. And now, give me a second. So we were doing some Z grading. This is technical, I'm sorry. And I want to pass to Z2 grading. And I should already have done that before the Pandari-Pandey Zvonkin thing. This is the grading, which is more common in coeft theory. This is very crucial for what's going on now. Otherwise, what I'm going to say is empty. And there is another problem or issue is that we need quantum version. So what does it mean? Well, I'm playing with graphs, which have genus, Feynman transform, etc. So you know that when you're doing this, you might have a divergence that you want to control, and then you want to introduce a formal parameter h bar, which controls possible divergence of some sum. Okay. Now, what can you do here? You can do kh bar extensions of what I said before. That's what you do when you do formal deformations. But no, there is something more subtle that you can do. You might want that h bar stands for the genus. Okay, so the kind of thing you can do is as follows. The kind of thing you can do is by looking at P. You do not change that. Circle ij, you do not change. But now you put an h bar each time you do the contraction. So now the powers of h bar keep track of the genus. Okay. So remember when we were doing the totalization, okay, this was giving rise to a shifted delta Lie algebra. Okay, let's say G associated to P. You can, of course, do this here too. Okay. And then now you can do G H bar of P, okay, which is what? Sorry, which is G of P. You do not change. You keep your bracket and you put an H bar in front of delta. And of course, this diagram is commutative. Okay, good, fair enough. But now when you have this, you can consider the quantum master equation. That is, now I have an extra h bar here. And of course, in some sense, it destroys everything because guys alpha that were solution to the master equation are not necessarily solutions to the quantum master equation. So now you are going to tell me I'm playing the wizard and, oh, I want to change the equations. Is there any example of that? Yes, yes, there are. Now, first, let me say that if I start from the shifted delta Lie algebra GA, which encodes homotopy coeft, and I consider this H bar, it's an H bar extension, but not a free one. Moror-Cartan elements, solutions to the quantum master equations, deserve the name of quantum homotopy coeft. Okay. Do we have example? Yes. We have example in Buriak-Rossi theory of integrable hierarchies. Okay. So do I want to describe that? Just a little bit. I just want to say that what do Buriak and Rossi have? What do Buriak and Rossi have? They have a functor like this. So Buriak and Rossi have already had this kind of structure without, say, noticing that it comes from a certain notion of quantum coeft. What don't say? Yes. So what can you do? So you see, if you start from, let me first say that you can consider lambda 0, which is 1, etc., until lambda j. So here I am considering some classes of mgn bar, which coincide, which are the Chern classes associated to the Hodge bundle. So you see, for the first time here, I'm playing with the classes of this guy, Chern classes of the Hodge bundle. Okay, and so what can I do here? You can start from the algebra I had before, which encodes homotopy coeft, to the algebra which encodes quantum homotopy coeft. And each time you have a certain alpha, so let me draw one which is quite simple, something like that, okay? Okay, then what you do? You associate to that something like this. So this class, you multiply it accordingly by lambda. This class, you multiply it by lambda, and you put h bar to the Betti number of your graph. Okay, so B1. I claim that this sends an element which satisfies the master equation on the left to an element which satisfies the quantum master equation on the right-hand side. Okay, so this is actually a morphism of shifted delta Lie algebras, and thus a morphism of the shifted Lie algebras. Okay, so it induces a functor of Deligne infinity groupoid. D'accord. And this is precisely when you restrict it to coeft. So when you restrict that to coeft, here I wrote a picture for homotopy coeft. But when you restrict it to coeft, when you start here from a coeft, that is just vertices, what the upshot you get here is the Buriak-Rossi construction. Okay. So now, yes, we can just spend 5 minutes, say, for the various symmetry groups. I think this can be explained in quite a short way, so let's try. Okay, so what is the opérade, SIGRA, that Kontsevich was considering? You're considering graphs, and since now here the edges have degree 1, and since you see the input output are symmetric, you cannot put 2 of them, okay? So for instance, I could have something like this. Okay, fair enough. So I'm considering graphs like this. I can have tadpole. So for those of you who know well the papers of Thomas, you can or not have tadpoles, okay, anyway. And the operatic composition amounts to plugging. So the circle I is what? You plug a certain tree inside a certain vertex. For instance, here, I equals to 2. Okay, so you're going to forget this vertex here, plug this one instead, and then attach in all the possible ways the elements here. So you have a sum over this way. Okay, this forms an opérade. Now, why this opérade? There is a conceptual reason for this operand. The conceptual reason is, well, it's here in blue. Now, first, let's notice that the totalization, I don't remember if I said that P hat is the totalization. So let me write it. This is the product of the PJN. So if you look at the totalization of a modular operand, it has a canonical Sigra algebra structure. Oh, so now on the totalization of a modular operand, we have two structures. We have the S delta Li, but we have a much bigger one because S delta Li sits inside this big operand. Delta is a degree -1 guy. Oh, that's the tadpole. And the bracket is this symmetric guy, okay? And there is a good reason for Sigra. S delta Li is the minimal operand which acts on the totalization of a modular operand and which allows you to write the master equation. Sigra, on the opposite, is the operand of all the operations acting on a modular operand, okay? So you have this in general, okay? The S delta Li structure on the totalization can be extended to this Sigra guy. But now we have a degree of freedom, which is great. So now we have this degree of freedom that the operations that we have here are not only S delta Li, but there is this full space off. So when we have a full space, we look at the deformation theory of that guy. So let me consider A, which is a def complex of S delta Li inside Sigra. This is a DG Preli algebra because it's a deformation complex of a morphism of a classical operand. Okay, and now we have it. We have the guy. We have the first guy, and there's going to be a second guy, and we're done. So the way we considered the thing on the left-hand side, what do we have? On the left-hand side, we look at what? We look at the even homology group of A, this deformation guy. We can equip it with BCH formula and 0. It forms a group. Okay, so this is a group. Okay, fair enough. Bon. This group, actually, when you use the methods of Merkulov and Villevareur, you can show that it produces universal formulas for, what do you have on the right-hand side? You take any Sigra algebra. Of course, the Sigra algebra I have in mind is the one associated to a modular operand, or my beloved one, which encodes homotopy coefficient. Curly MC stands for the moduli space of gauge equivalent Maurer-Cartan elements. Okay. And then what this says that you have a morphism of group from the left to the right. That is, you have a universal action of this H even A to gauge equivalence classes of Maurer-Cartan elements of a Sigra algebra. Okay. Bon. Alors, let me give an example on the right-hand side. Let me say what is the shape of the guy on the left-hand side. Left-hand side, but it deserves a name. It's a group of universal symmetries, universal deformation group. This guy is actually admits, so for instance, if you look, you have this tetrahedron inside G. I need you to do this computation. And now this guy admits some cohomological degree. Okay, you can introduce a certain cohomological degree and you can compute. And if you look at the paper of, MW means Merkulov-Villevareur, the cohomology zero part is GRT1. Oh. Negative degree, nothing, and higher up, very interesting stuff. If you can compute G1, that would be lovely. Okay. So what does this say? And did I write much? No, good. So what does this say now? This says that on the left-hand side here, you have what? You have at least, so let me write example. Here you have at least GRT1. But please, keep in mind that this definition is very general and universal. We are happy to find GRT1 at degree 0. It would be lovely, but nobody knows how to compute this. What is G with positive cohomological degree? So GRT1 acts on the gauge equivalence, on gauge equivalence of homotopy coefficient. Alors, of quantum homotopy of T. But this holds in general for morphism of any modular operands. Okay, and this, you see, this action is universal, is functorial and is with universal formulas. Okay, now there are two things I want to say. You can try to do two things. One, say, oh, but there is an H here. Oh, sorry, there is H bar. What can happen if I forget about the H bar? Maybe I can specify it at H bar equals to 0. So remark, you can maybe put H bar equals to 0, 1, no 1, sorry, which means that you're looking at genus preserving maps. Okay, but if you look at that, the theory is trivial. The even homology is 0. Well, it's one-dimensional. H even now is equal to K, and the theory is trivial. So no, you need the quantization here. Okay, that's why I was considering this. And of course, I'm low on time, so I just want to mention something. Because I said Telemann and Giventhal. So here I have not been using. So you can do the same thing now, reproduce the same argument, do the same thing with, well, you see, here when I considered SIGRA, I never played with any classes of MGN bar. I was just doing a general universal theory for modular operas. But now I can ask myself, you see, SIGRA is the universal operad which acts on totalization of modular operad. But now let's say I want to coin a universal operad. So you introduce a universal operad, no, an operad of universal operations which acts, now not any shifted delta Lie algebra associated to an operad, but GA. Okay, so then your operad is quite simple. It's, let me call it tot gra. It's an operad of graph enriched with tautological classes. So it looks like something like, okay, so the same kind of operad I had before. But then you can, and since I'm low on time, I will not do it explicitly, label it with some classes, etc., that comes from the cohomology of your guy. Okay, so the mojo is you can enrich gra into some taut gra by adding some tautological classes. So of course you have your SIGRA which sits inside that, so when your tautological classes are 1, and of course you have shifted delta Lie which sits inside here. Okay, but now if you do this, the depth theory of this map gives rise to a bigger, so you do the same thing as before. Yes, you see. So instead of putting SIGRA here, you put taut gra. Okay. Then you're going to have a guy which acts on the gauge equivalent classes of quantum homotopic OFT, exactly in the same way. But the guy on the left-hand side, whoa, gets much bigger. And so we were able to compute part of it. And now H even, contains Grothendieck-Teichmüller group, GRT1, and Giventhal group. And okay, I know I did not define that, and I'm stopping here. I just want to say that, say you know nothing about Giventhal group, fair enough. And you just consider this story. This has nothing to do with Giventhal. We were actually able to recover Giventhal's definition from this method. Okay, the exact same group, the exact same formula. But the bright point, if you want just one interesting application, yes, we were able to recover Giventhal action, but Giventhal action is on cohft. Well, our our story works for any quantum homotopy coeft. Okay, and why could that be interesting? Well, let's say you want to left the Gromov-Witten invariance from homology or cohomology to the chain level. You know by abstract nonsense that it should carry a structure up to homotopy. So here is a definition that we propose. Here is the definition of homotopy coeft. And here is, for instance, an action which we know generalizes given tal action on homotopy coeft. And if you feel motivated and you still have a few days of holiday, that would be great if you could compute this group for us, okay? Because this is just the G0, okay? This is just cohomology 0. What is in positive degree, we don't know. This is very, 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 very complicated. Okay, thank you very much for your attention.